So the topic for today is CMOS VLSI design, challenges and opportunities. And again, since I am from industry, of course, I'm part of academia, but this is mostly from a product design perspective. How does the VLSI help us to design products that we see? So, and that will be the focus of my talk. The agenda here is let's understand why VLSI is a hot field. Why is it? Why do we keep hearing about it now? Last 1.5 years, you would have heard a lot of buzz on the semiconductor manufacturing. Government of India is also focusing heavily on indigenizing the electronics, and then we talk about VLSI technology challenges. I'll briefly talk about IC design flow, understanding application requirements, and followed by hopefully we'll have some time for a few question and answers. Okay. So I would say the theme of the talk, if you have to keep a central idea in mind, is that for whenever we talk about VLSI design, right, let's think of one statement that I mentioned here. How do I guarantee that 1 billion devices designed and manufactured today remain working in application for the next 10 plus years with acceptable performance? Now, it's a very profound statement. First, guaranteeing that first of all, we design and manufacture 1 billion devices. Why? Look at the number of phones that are being sold. I mean, every 6 months, every 3 months, there are new models, and the number of phones are the IoT devices, the number of phones, the number of consumer goods, the smartwatches. All of these are really outnumbering the number of population. I mean, if I think there's a study that says we have 3 times more electronic devices than the population of the entire Earth now, and it's going to become 4 or 5 times in the next 5-6 years. So this means there's a requirement to design and manufacture billions of such devices. Now, once we do it, right, and there is no time machine, somehow by design, we need to guarantee that whatever we are designing and testing today is does remain working in the application for the next 10 plus years. Why? Smartphones, you might probably change once in 5 years or 3 years. Cars, where you see a lot of electronics coming in these days, you don't change the car in 3 years. You probably want to work for 15 years inside. The application needs to work at least for 15-20 years. Now imagine what happens if you go to a space satellite. It's a lot more number of years, and then the robustness, the acceptance level, the safety level for the device needs to be extremely high. Just for one interesting thought, you would have seen the Chandrayaan-3 launch, right? Some of you would have realized that when there is a lunar night, so this means when there is no sun, Chandrayaan-3 stops working, and now people have tried to wake up again. It doesn't work. The main reason, if you don't know, is that when it's a lunar night, the temperatures on the surface of the moon is minus 150 degrees centigrade. I'll repeat, minus 150 degrees C. Okay, so to make electronics or to make systems work at such a low temperature is extremely difficult. I don't think we have a viable technology, and that's the reason why the devices don't wake up, because it reaches the end of life. So that's why they have to time this, the travel to Chandrayaan and so on. Okay, so first topic: why is VLSI a hot field? Now, to start with, whenever we want to, let's say, do something, right? We talk about VLSI innovation or VLSI design, or any researcher this is also applicable to any researcher who is starting on his PhD or master's thesis, or anybody who is working in industry. First of all, your work, you have to be clear about what is the motivation and purpose, who needs it, and what are the use cases. So this will help. Where is your design going to be used? Which use case? What are the boundary conditions? And why is the innovation or the work important now? And is it affordable? And is it scalable and sustainable? Okay. All these are some thoughts that we need to keep in mind before we go into any R&D work or a product development. Okay. Now, let's start with a little bit of history. So, as you probably know, the VLSI stands for Very Large Scale Integration Evolution. I believe most of you would have heard about this term. So, the first computer, which was invented back in 1946, right? It's called E. This was the size of almost 1800 square feet, like a typical 3 BHK flat size, and then it was weighing 27 tons. And from there, people have started realizing that it doesn't work out this way. So there needs to be a way to make So we integrate more and more circuits. We have multiple devices on one single substrate, and then people coined the term of transistors there. We have memories. We have these processors that are being designed in 3 nanometer, 5 nanometer technologies. Build almost like hundreds of millions of transistors. So from an 1800 square feet a room for a first computer to the right side is a GPU that was released by a company called Cerebras. This had about 1.2 trillion transistors. Okay, 1.2 trillion transistors in number 90. Look at the evolution that has happened from 1946 to 2019, the amount of scaling, and this is purely possible of the shrink that the technology provides, the way we are able to smartly use the creativity of the designers to be able to densely pack the circuits which can cater to multiple applications. Okay, so what was a 3 BHK flat size is now as small as this single integrated IC that you can hardly see on the finger, right? So let's understand what drives VLSI innovation, right? So on the right side, if you see, I think it's probably Samsung S5 or S6 number. You see these two tiny dots here. So this is the transmitter and this is the receiver. What does this do? You see that whenever you get a phone call, as soon as you place the phone, the display shuts off. And this is essentially because you want to save power. The display is the biggest source of battery drain in your smartphone. And while you are speaking, you don't need to see the phone. So something inside the mobile phone, some kind of a sensor that will detect that there is an object within a certain close to the phone. It'll shut off the display. As soon as the object moves away from the phone, then it display turns on again. So this is the job of a typical proximity sensor. And if you go inside what's behind this, you can see this small, it's an actual photograph of the sensor. It's tiny package. The of this is 1 mm by this is 1 mm, this is 2 mm, and the height is about barely 1 mm again. And what's there inside, you can see that there is these are the two holes, and on one side you can see LED or a VCSEL which is emitting your IR light. So by the way, which is the most common IR LED that we see in our houses? A remote control. It's if you switch on the TV, you press, and then the IR LED is emitting its pulses. The TV receiver detects this and it does the job, whatever you want it to do. So this is similarly, this is an IR LED or a VCSEL which is sending out, and the reflected energy is sensed back into the receiver, and this is the receiver. And inside the receiver, you can see a very, very tiny small block, which is the tiny sensor that is sending the light into an electrical current. And the farther the object, weaker is the reflected signal, hence smaller is the current. Closer the object, stronger is the reflection of the pulse, and hence higher is the strength of the electrical current. So looking at the strength of the current here inside this, you are able to determine how far or how close the object is. If you just look at this, right, now you can imagine the amount of integration that goes into it, the placement, the aperture, the packaging, the design, all of this coming together in area of 1 mm by 2 mm. That's what we are talking about, VLSI innovation. So first, what drives VLSI? High performance. We need better quality of products. We need smooth, silky touch smartphones, great response, longer battery lives, lower power consumption, obviously because we need a longer battery life, digital scaling, and then higher integration because we want to pack more and more features. This means we need smaller size of our integrated circuits. We want portability so that we can hand carry these. Our mobile phones, we don't like it to be too large. We want it to be portable. We want it to be reliable. Of course, lower cost. Higher volumes, mass market deployment means that we cannot have a prohibitive cost. So anything that we design should be with a mainstream technology, a mature technology, so that we can minimize the cost. Then smartphone deployability. So this is one of the biggest drivers for semiconductor growth. Anything and everything you see here, including, let's say, oxygen sensor, heart rate monitoring systems, camera identification, face ID, payments, everything is going into the smartphone, because that's the biggest driver for the semiconductor growth. The number of smartphones being sold across the world outnumbers any other electronic good, and that's why everybody working in this electronics domain wants to get a share of the pie. So they want the products to be compatible. They want to see how they can deploy in the smartphone, so on, right? And because of this, CMOS is still considered as the mainstream technology. So you would have heard about FinFETs, you would have heard about compound semiconductors, and then, but overall, I would say for manufacturing perspective, CMOS is still the mainstream technology, and that's why it's very relevant to understand about the CMOS design and technology. Okay. First of all, different specializations of circuit systems before I go in detail about the VLSI part. So I just had a power cut. So am I audible? Can somebody confirm that you still see the slide?
Yes, sir, you're audible. We can
Okay,
see.
great. Yeah.
Yes, sir.
So to understand about the field of the circuits and systems, right? On a high level, what all are included as part of this CAS? First is analog. So analog essentially deals with interfacing with the real world, power management, and so on. So first of all, anything that you see here, like an audio frequency, touch, temperature, light, sound, all of this heat, all of these are analog quantity. Because if somebody asks you what is your room temperature, you don't say it is 100011. You say it's 25 degrees. That's an analog quantity. So people who think that analog is not going to stay, it's all going to be digital. Anything as long as there is a real human interface to any application, analog is going to stay. And without analog, there is no human machine interaction. So the interfacing with the real world is always through analog. And then all these digital circuits, the processors, all of them need power supplies. And the main power supply is coming from an analog. If you have a 5-volt supply or a 3.3 volt or a 1.8 volt, car battery which is 14 volts, a mobile battery which is a 4.1, all of them are these power management circuits that deliver power to these to the entire application or chip are predominantly analog circuits. Okay. Then comes the digital. So the beauty of digital is that once you convert something into digital domain, right, it's very difficult to disturb or it's much more immune to noise, external noise. And hence you can peacefully do a signal processing. You want to do filtering, you want to gain it up, you want to add, you want to multiply something. All of this is extremely easy once you go into a digital domain. So the advantage of digital is the noise robustness you give. You can, if you have, let's say, 1 volt as an analog output, you can disturb that 1 volt to make it 0.9 or 1.1 volt. You can disturb that, adding some noise. But once you have a 0 or 1 in digital domain, right, it's very difficult to make a 0 into 1. You need an extremely insane amount of energy or disturbance to do this. That's why the digital circuits are more robust. And of course, with the scaling, technology scaling, you can do a lot of signal processing to make sure that your application is meeting its requirements. Then we have a third one called RF. RF stands for radio frequency. This is essentially a high frequency. Think of it like a high frequency analog. So all our wireless signal transmissions, the GSM mobile network, the 900 megahertz GSM network, the Bluetooth 2.4 gigahertz, wireless LAN for 5.2, 6Gs, 5Gs, all of them fall in this category. So the RF radio frequency circuit design. It's also a very, very exciting field. Then we have embedded. So embedded is more like a kind of a hybrid between software and hardware. So you write a code into a generic hardware to make it do some automated tasks. So this is the job of a firmware. Here you have microcontrollers, microprocessors, field programmable gate arrays, field programmable analog arrays. All of them fall under the embedded category. So this is like the combination of multiverse of software and hardware. Then we have memory, a very important part of it. We all take our purchase decisions based on the memory. How do we have 128 GB in my phone, 256 GB? I want 512 GB. Better cameras are making sure that we are creating large videos now, and then we want to store them somewhere. So the data storage, data retention, retrieval are all part of this memory segment. and the DRAMs, SRAMs, RRAMs, memory star RAMs. All of these are a very exciting field of research. Then of course we have EDA. EDA stands for Electronic Design and Automation. So this is how you model the whole analog, digital, or memories, all of them on the computer using a certain tools, certain models in the background to make sure that you're able to design on the computer, verify that the design meets the requirements before you send it to manufacturing. So all Cadence, Synopsys, SmartSpice, MATLAB, Python, all of this fall under the EDA category. Then we have testing or validation. So this is the real world stuff. Once you have the whole thing designed and once you get into the lab, how do you characterize the system? How do you make sure that you can do electrically the validation? You make sure that it's meeting all the requirements. Thermal characterization, which means a mobile phone that's you're designing a circuit. That circuit should operate whether you're talking on Himalayas, or a mobile phone should operate you're talking on Himalayas, or whether you're talking in a Sahara desert, right? Extreme temperatures. So the device that you manufacture needs to be tested across extreme thermal conditions. And there are some niche applications, like I just spoke about an optical sensor, where you also need to do an optical characterization. Okay, and with one of the exciting things about this testing validation is also that there's a lot of automation. It's not gone are the days where in the lab where you might just be doing, let's say you take a breadboard, you fix an IC, and then you want to test it and then see that the circuit is functional. Now imagine if you go with this type of speed in testing millions and millions of ICs with several applications. It's impossible to do anything less than 10 years. So each IC would take more than 10 years to test it. And now with mobile phones changing every 6 months, we have a requirement to kind of do an automated testing. There's high-end robots that are employed to test these circuits, and the testing of these are done 16, 20, 32 of them in parallel, and they're done in seconds. All the complex testing is all done in seconds, and that's the job of an AT, automated test equipment. And very, very exciting work that's being done in the industry as well on this ATs. Last but not the least, production. So production talks about mainly we deal with reliability, failure analysis, ESD, EMC. So reliability is essentially what I spoke about. How do you make sure that the circuits designed today are still functional? How can you predict the performance of the IC 10 years later? Okay, this is about study of reliability in the circuits. How does it? What is the degradation you would expect in the circuits, and so on. So one easy way to understand reliability is, if you go to a cardiologist, somebody does a heart checkup, right? They ask you to do a TMT test, treadmill test. And the treadmill test essentially is, you are asked to run on the treadmill at a certain speed. They increase the speed. They have all the electrodes all around your body, and then they monitor the response. Okay. So what they're doing is they are stressing the heart beyond the natural operating regime and seeing how the heart behaves and how the heart is able to recover back from the stress. Apply the same logic to your circuits to make sure that your circuit is able to work for a certain amount of time. You have to stress the circuit. And how do you stress it? You can do a temperature stress, you can do a voltage stress, take it beyond the general operating conditions, let it be there for a certain amount of time, and now start back calculating. You use some models to back calculate and see if a circuit is behaving within these limits for this temperature and for this amount of time. Then for a lower temperature and for the circuit will be functional for maybe 10 years or 15 years. So this is how the reliability calculations are working, and very interesting and niche field as well. Next, failure analysis. This is, I think, one of my personal favorites. For somebody who's coding on the computer, right? It's very easy to say, okay, I code it, I run the code, I compile it, I get a compile error. I can go back and check my code, rerun it again. Okay. Now imagine apply the same logic to a hardware. You've designed something, sent it for a manufacturing, you got it back, you powered on, and suddenly nothing is working. Now what do you do? So the whole concept of failure analysis, analyzing why a circuit or a transistor is not working, and then going inside these hundreds of millions of transistors to identify why exactly a certain location has a problem, is an art in itself. Very exciting. Go through almost just the way you take an X-ray of your body to identify a broken bone, right? The entire IC with the several metal layers, there are X-rays that are done, failure analysis that are done. So it's very cool. The whole concept of failure analysis for an integrated circuit is pretty interesting. ESD, electrostatic discharge. This can damage our circuits. You can see almost tens of thousands of kilovolts generating for an instant of time that can get discharged through your IC. So you have to protect your ICs. EMC is electromagnetic compatibility. This is the reason why air hostess asks us to shut off our mobile phones during the runoff or takeoff or landing. That's because the electromagnetic emissions that are getting emitted from the electronics can disturb the controls. So EMC is a very important part. And then yield. When we are designing 100 million phones or 100 million circuits, 1% yield loss is like 1 million bad devices, which is a huge number. That's why the goal of every product company is to make sure that you maximize your yield, get it to the order of 99.9%. So which means these are good circuits should be as large as this. It's a very overall, you can see it's a very exciting field with different specialization, and each of these will have sub specializations. I mean, that's, I'm not going to go into detail on subspecialization, but at least this should give you a feel of what all are there in our circuits, and then you should be able to now correlate better to what you study in your classroom. Some of you should be able to map what you study into some of these. Now, about the VLSI technology challenges. CMOS technology section, of course, we know there is an NMOS transistor, then there is a PMOS transistor. NMOS is built in a P substrate. You have N-well, then you have contacts, you have polysilicon gate, and PMOS is built in an N-well, and you have all of this. So now, in addition to PMOS and MOS, if you do a cross section, right, what you now end up with an actual full-blown menu of a CMOS technology typically gives you this. You have an NMOS gate, a polysilicon gate, followed by your drain and source. And then these source and drains are now connected all the way to the outside world using different metals. These are the electrical connections to them. Similarly, a PMOS is built in an N well. You have a P plus source and drain extensions which can be connected through the drain or source. I mean, the very interesting thing about this is, see, this is like not only electrically, right? This is also mechanically. This circuits need to be very stable. So imagine this is like it's like each floor. Metal one is your substrate is your ground floor, and then you have metal one which is first floor of a building. Metal two is the second floor of your building, and then so on. And they are all connected. Now, unless your foundation is strong, and think of these vias as pillars, right? So unless your foundation is strong, it's possible that the whole thing can crack. There's a lot of mechanical stress that goes on the substrate just because of the way you're manufacturing it, and all those are very important to study. Even the mechanical the stress on these circuits are a very important and exciting field of work as well. So in addition to these transistors, you also have you need resistors, passives. You can manufacture resistors using a poly. You can manufacture using an N-well resistor. And there are capacitors, of course. You can do a metal insulated metal capacitor, MIM capacitor, or you can do a poly capacitor. So if you think of a conventional capacitor as two plates with two terminals, in an integrated circuit version, you will not only have two plates and terminals, but there is going to be a parasitic capacitor. As an example, for example, let's say if you think of a capacitor like this with one terminal A and B, for a VLSI engineer, this means that not only you have A and B, there's going to be parasitic capacitance to some other nets. There are going to be parasitic capacitance on the bottom plate as well. So this is now becoming a distributed network. Similarly, for a resistor for a VLSI engineer means you can have parasitic capacitance across this. You can have parasitic resistors here. You can have substrate capacitance across this. So it's a much more complex distributed network. And that is what differentiates between a conventional design versus a high performance VLSI design. Because of the way the whole circuits are fabricated, there are going to be these parasitic elements that come along with your ideal element, and that is what makes the whole circuit design or a VLSI design very interesting. Okay, so what are the challenges in an integrated circuit? Once you go into the integrated circuit design, there are because you have to manufacture them, and this manufacturing process has a certain variation. They have their own the lithography machines that you use, the material, the purity of the material. All of them lead to certain non-idealities. Nothing in the world is ideal, so there are always a certain tolerances for any equipment or anything. That's the reason why there are also going to be some variations of the manufacturing process, and which leads to variations in the threshold, variations in the channel length, and a variation in interconnect dimensions, which leads to, let's say, some extreme cases that we have to think in terms of. If you draw a graph where you see x-axis is NMOS, a slow NMOS means your VT of your NMOS is high, a fast NMOS means VT is low. The VT is threshold voltage. So threshold voltage by definition is the amount of voltage needed to start a conduction, so start a good conduction of a electrical current. Similarly, if you have PMOS and NMOS, you can see that now you can have 4 different combinations: a slow combination where your PMOS and NMOS is slow, or a slow fast, fast, and fast slow. All these extreme combinations, by general principle of monotonicity, if you ensure that your circuit works well under all these conditions, then normally they should work under the all inside the boundary conditions here. Okay? This is about the process. In addition, you also have voltage variations. Now, whatever is a power supply that's coming to your circuit can vary by 10%, because these power supplies are all generated again by some more circuit outside, or a DC-DC, or an LDOs, so on. So though that's another, so you need to worry about the voltage variation. Typically plus minus 10% is a good number. So which means if you're designing something with 1.8 volts, please consider plus minus 10% variation as a feasible thing, and you need to make sure that your circuits are simulated for this. Then of course the application, temperature can go, for a consumer application, you can go 0 to 125, or in fact, you can see here that commercial applications it's 0 to 70. For industrial applications, it is minus 40 to 85, and for military grade applications, you need minus 55 to 125. So this means the same circuit, same op-amp, same filter designed across different applications would mean different design challenges. Okay. So last but not the least, aging and wear out. So you can also see that the aging, the transistors, they age over time. Like human beings, transistors also age over time because of hot carrier effect, because of negative bias, temperature instability, time dependent dielectric breakdowns. All of these cause threshold voltage change. So over a period of time, your threshold voltage, whatever you've designed, changes, and we need to make sure that we anticipate the amount of degradation in the threshold voltage through these models, and then consider this design margin so that the application still remains intact. Okay? So nothing is constant in an IC in absolute terms. We need to understand. The only thing that works well, or an agreed principle, is that 2 transistors which see similar conditions, similar environment, similar neighbors, similar sizes, they behave similarly. So this correlation is what is helping the whole VLSI design, the analog design predominantly, is how smartly can we match the transistors to give us the required functionality. Okay, and like I mentioned again, like a typical treadmill test that we do to find out the health of a heart, we have to also do accelerated life tests to find out the health of an IC. Now, what is an IC design flow on a higher level side? If you look at a process of digital design, you start with many different levels of abstractions. So this means you can start with a high level system design, which includes architecture or an algorithm level design. So let's say you want to find out a second derivative of some. You're designing an ECG monitoring circuit, so it will tell you that if you monitor the electrode and you take a second derivative of the electrode, and that is going to tell you whether your systolic pressure or diastolic pressure is high or low. So this means on an algorithm level, you're saying, okay, if I do this algorithm or some processing, that is going to give me the information that I want. From an algorithm, inside the heart of the algorithm is basically the system level design from the digital side. Okay, so here you can have a module level design, then you have a gate level design. Finally, so module can simply be like an adder here, and in the gate level design, it could be our logic circuits, like AND gate, NAND gates, and so on. If you go inside this, it's going to be again a transistor level design finally, which is as an example, inverter, you can have an NMOS and a PMOS transistor. There is a load, there is an input, certain fan out, you have supply, you have ground. And then if you go a little more, the core of all of this is basically your device. Again, source, drain, gate, polysilicon, contacts, all of this. So be it the digital design or an analog design or an RF design, fundamentally the device part, the core of that is the same. the level of abstractions we use is going to be different. We probably, I mean, when you talk about a Verilog coding or a VSL coding, you might be dealing on an abstract level, right? But finally, when you get to the actual design, actual circuit, you have to deal with the challenges that a typical device gives you on be it in digital design or an analog design. So analog IC design flow, you're basically trying to think of the application, build a block level system design. So this means do a high level Verilog game models, or you can do a MATLAB, or you could do in fact, you could do even a Python scripting, or you can do in Cadence as well. Just do a block level design where you assume that you have these blocks like an amplifiers, OTAs, the comparator, the diode, all these passives, all of these are available. Simulate the circuit, and then if the circuit is working as expected, then you start designing the individual component. For example, if this works, then you know that, okay, I need this much gain from the amplifier. Now you go back and you design the components. You do a transistor level design of those individual modules. Again, you replace this behavioral block level module with the transistor level module and resimulate, verify it in simulations. And once you're convinced that it meets your requirements, then you do a physical layout, physical design, which is basically synthesizing your netlist for digital folks, or you could be doing a custom analog layout for where you do transistor by transistor connections, you match the transistor, all of this, and finally generate a physical representation of layout. So what does this layout do? It's basically metal by metal. You're telling how to manufacture this, where you have to connect. It's basically footprint of a building. What is the ground floor? What does the first floor look like? How are you connecting ground floor to first floor, and then so on? All of this physical representation of your IC is what the whole layout or a physical design is about. Once you have done this, now you need to manufacture it. Okay? You have to send it to manufacturing, build the circuits, and there the way to manufacture this is that I'm going to go through this process as well. So you first fabricate this. You generate these dies. Here, this is one circular wafer where you are generating all the different dies, and these dies perform a certain function. So this is where your circuits are. Now you slice all of them. You slice vertically and then split out all these tiny rectangles, and take these rectangles, embed in a package, and then put the package in your application board to connect power supplies and see whether it is actually doing the job that you expect it to do. So this is basically the concept of IC prototyping. So the verification, the simulation that you've done on your computer, now you have to repeat this on the actual IC. So you have to characterize the IC, apply the appropriate stimulus, look at the outputs, characterize the output, and then once you have it, you build the evaluation board. You're convinced with the evaluation board, with all the connectors, interface, everything. You can now start building the products in the application. So this is the whole production flow, and with a little more details on the manufacturing, you can generate the wafer through. If you learn through a semiconductor design course, you would see that the most common process is the Czochralski process, where you have a melt, and then it's basically the seed crystal is rotated slowly from this. As you grow the crystal, you kind of make a cylinder, a large cylinder, and once this is there, these large cylinders are there. You slice them into thin slices. So that's what is giving you a single wafer. So it's like slicing tiny wafer slices from a big potato, right? That's how you would do from a big ingot. Once you have that, you saw it, and you create all these individual wafers. All these individual wafers are created, and once the wafers are created, you generate these master slide set masks. So this is telling you, okay, how the circuits are looking like. Each layer, like ground floor, first floor, second floor, the polysilicon, metal 1, metal 2, all of these each levels are mapped to a master image of a slide set, and now use UV light. So this master slide set or the mask is typically like the mask used for to prepare the Ganesh idol. So the outermost shell, that's the stylus, right? So you put a material, it takes the shape. So similarly, you have the master slide set, and using light, ultraviolet photography, you can make an imprint, a very tiny imprint of this master image onto your die. So this was your wafer that you had. Now with high precision UV light, this is called lithography. You can now make a very miniaturized stylus here, imprint on the glass reticle. And this, once you do at all the layers, will give you a final wafer which has all the circuits. So this is one wafer where you have all the circuits imprinted on it, layer by layer, okay, using different stylus. And This is the assembly. So finally, the wafers are very brittle. They are very tiny. They're brittle. So you need some mechanical support. So and that mechanical support is given by the package outside. So you can see that this small die is now embedded inside this package, and you have to do electrical connections. So the small, very, very tiny electrical connections are done to this and packaged. The outer part is what you see here. These are thick leads that you see outside, and eventually you would end up with a IC like this. So these are the pins that are connected to the outer world, and this is the package. This is the backside ground connection, and once you solder onto it, the circuit does the magic. Okay. So in short, this is this is how the flow of this whole integrated circuit manufacturing flow is, and that is what gives you this IC, SOIC, and this is what we see in our labs. If you go to a electronic device circuits lab, you directly pick this component, solder on the breadboard, and then you give the stimulus, connect passives, to make your application. And those of you who are interested, and if you're allowed, you can nicely slice this, put 1 or 2 drops of acid on top of it, slice it out, decapsulate this, and what you see now is this one. Once you take out the outer shell, right, you can now see that the die that you've sliced from the IC are now connected through very tiny bond wires, and that are now connected to the external pins. So this is how, from an external world, your supplies, power supplies, grounds are getting connected to the transistor through the pads, and then the transistor, this VLSI circuit is now doing its magic and giving you the required functionality. Okay, and also important thing to learn is that these days you're not spending a lot of time in the lab doing manual validation testing. You build these, you use this FPGA boards. You build a validation board where you can control the stimulus using an FPGA board, and then you can even automate power supplies, the multimeters, the oscilloscopes that you all use in your lab can all be controlled using a lab view. It's all, nobody's in industry, nobody is now doing a manual testing, right? Everything is automated, so you can literally, the whole testing process is all done to the computer, where you can control the instruments using a GPIB cable, and then the power supply will give you the voltage that you want. The oscilloscope is measuring it. Thermostream is applying your temperature that you want, and all of this data is collected and then analyzed, everything through the computer. Everything is automated. Okay, so that's, I would say, the IC design flow, the manufacturing flow. Last 10 minutes I would like to spend on understanding the application requirements. Okay, first, whenever we do a product design, first thing to understand is what are the required accuracies. What is the resolution of your input signal? What is the bandwidth? What are the noise requirements? For example, if you're designing an audio front end, okay, or a microphone, a MEMS microphone for an audio front end, you know that the audio signal is between 20 hertz to 20 kilohertz, right? So anything more than that, you can always reject it. So this is basically your bandwidth of your signal. If you're doing a temperature sensor, then the temperature does not change instantaneously. So the bandwidth of a temperature sensor is typically very low, maybe not more than a few hundred hertz. So similarly for the temperature range. So it depends whether are you designing the circuit where if you're trying to come up with some an engine control unit, and the IC is expected to be close to the car engine. Now you can imagine the location close to the car engine is going to be very, very hot. So this means the ambient temperature seen by the IC is going to be higher, and you have to simulate for it or design for it. In addition, if you are using a high current system, or you're using some gate drivers or high power consumption systems, then there's going to be a self-heating of the IC. So this means while you're taking some energy from the power supply, not all energy is getting converted into a useful electrical load. There's going to be some wastage which converts themselves as heat. So every IC experiences, when I say an IC, it's an integrated circuit. Every integrated circuit during its function of operation experiences a self-heating because of the loss of energy. So for high power devices, we have to worry that for the final junction temperature, the transistor temperature that it sees is the sum of ambient temperature plus the temperature increase due to self-heating. That's why it's very important to estimate both. Of course, power consumption is very important. Are we doing a portable device like medical electronics? If you're trying to design a pacemaker, most important thing is the reliability and also the current consumption, because you don't want to change your pacemaker I mean, every month or so. So you really need to keep it working as long as you can, 6 years, 7 years, 10 years. That's why the current consumption of these pacemakers are very, very critical for all these applications. Of course, there are some other applications where you have a nice large car battery, you're doing something in the car. So there, and the power consumption might not be such a high priority. The performance might be a more bigger priority. So for a specific application, you need to understand what is the important parameter, what are the key considerations in the application, and then optimize your design accordingly. Fourth is economics, how to minimize the cost. How do you partition the system between analog, digital, RF, memories? What are the choice of external components? How big, how small? What is the size? Because if you want to, let's say you want to pick a 100 microfarad capacitor, it's going to be very, very large. And you want to make very tiny electronic system, you cannot have a 100 microfarad capacitor lying on there, because it's going to be very bulky. So your choice of components, the value of component what you pick, plays a big role in not only the cost but also the size and form factor of the PCB. Similarly, the quality. How do you test the system in the lab? How do you monitor the health of the design and device while it's working? So can pacemaker can it give you diagnostics? Can it give you a health of the device? Like a typical battery. All our smartphone gives is indicating the health. Right? It tells you that the charging is only 15%. Please charge quickly. So it is giving you the indication. So like a smartphone, there are many other things where it can give you the health of the device, health of the battery, health of the overall application, and also how do you guarantee the lifetime of an IC? I just discussed. We need to make sure that the circuits work for their entire lifetime. Robustness, ESD, protection, latch up, EMI, interference, immunity. All of these are critical requirements to understand and then plan your circuit design. Okay. Now, I'll give you one example of a smartphone which we all know. Okay. How does VLSI designers start thinking in terms of the requirements? Let's say as users, we all use smartphones. We are end users of this. What do we expect from a smartphone? Right. What we want is basically a thinner size. We want sleek smartphones. We want less weight. We don't want to carry bulky phones. We want great battery life. We don't want to charge them often. We want the battery life to last longer, very reliable. Even if the smartphone is working for 4 years or 5 years, it has to be very reliable. The touchscreen needs to work properly. Battery needs to be good. Then, of course, last but not the least, very affordable. Right? We don't want to pay huge sums of money for a smartphone. So these are the requirements as users, okay? As end users of the smartphone. So what does this translate to an electronics engineer? Okay. So what this means is that we need to have small form factors of components. So smaller sizes, small thinner PCBs, smaller form factor of the integrated circuits. Of course, less number of external components, and this is the motivation to integrate more and more. You integrate more and more in a single chip so that you can minimize the number of components, minimize the number of connectors. Have plan for low power modes. Design integrated circuits with low power consumption to maintain great battery life. Monitor the battery that is constantly diagnosed, and also think of self-healing circuits, PVT compensated circuits, PVT invariant circuits, all of these, so that they don't the variation or the lifetime degradation is significantly smaller, and we have to guarantee that the lifetimes are meeting the application requirements. Now, what does this mean for a VLSI engineer? The electronics engineer is telling you, okay, boss, I need low power modes. It's your headache. You do whatever you want. For a VLSI engineer, what this means is that when I have to do a small form factor, we have to plan in the device technology to think of through silicon vias. We have to shut down, make ambient light sensors for adaptable display, proximity sensors to turn off the display, MEMS microphone with excellent noise rejection, fast battery chargers, DC-DC converters. This is one key point that every smartphone manufacturing is advertising. 10 minutes charge, and for your half a day, the whole thing, charge your phone in 10 minutes. So you need fast battery charges. AMOLED, OLED screens for better contrast ratio. It's an organic LED display, which is again these TFT LED monitors are all basically transistors, set of transistors. Then time of flight based cameras for objective focus, high sensitive capacitor touch screens, fingerprint sensors, face ID, payment gateways. The list is never ending. So now you see that now you can see how the user requirements is now translating into electronic requirements, which is now again translating into a VLSI requirements, and that's how the whole thing gets designed. And one application that we all know is I spoke about this, that as soon as you have your phone call and you place the phone close to the ear, the display shutting off. Okay? This is the job, as I mentioned above, is done by the proximity sensor before, where you have a transmitter and receiver. Now 6-7 years back, I think this was probably S5, it was cool, you had some space to embed this. This is doing its job, we had everything was working fine. But then over the years, as users, we don't want to carry large phones, but we want to see large videos. And how is this possible? This is only possible if the ratio of the screen to body is now increasing. So this means your entire body needs to be screen, so that I can watch, take good photographs, look at, watch movies on the phone and so on. So this means the space that is available to embed these sensors, electronics, is now reducing. So over a period of time, people have come up with all the requirements. So this is the OnePlus teardrop design that you see here, and then smaller and smaller. Now imagine all these sensors that had space earlier, the selfie cameras, the ambient light sensors, the proximity sensors. Nowadays there is absolutely nothing. There is no space, because the entire screen entire body needs to be a screen. This is where the challenge comes in for VLS engineers. How do we make sure? How can I miniaturize the whole sensors? Where do I embed this? How smartly can I handle the application? And this means that essentially we need to shrink the size of IC, improve the performance of IC, of course, reduce the cost, improve the reliability, reduce power consumption. And this is what giving the challenges for generations. For each generation of phone needs to have a certain improvement. We need to improve the performance. We need to improve the signal to noise ratios. We need to reduce the overall size, the physical size of all these sensors. Think of smart ways and creative ways to embed these sensors. Okay, so typically this is how you can see that application specific challenges come into play. Okay, and one of the other technology advancements that has happened over the years is that unlike a two-dimensional PCB, where if you want to build more and more features, right, you have to grow the PCB. But instead of that, people have started smartly doing thinking of interposers, where you can have different ICs that are molded on top of it, and then using a small interposer, they are connected to micro PCBs. Next level is called as 3D integration. So this means you are actually stacking the dies rather than expanding in one dimension. In 2D, you are expanding in 3D, so that the physical space you need, the space you need in the package substrate of the PCB, is now becoming smaller and smaller. And this is possible because of a through silicon technology. So that's called as 3D IC integration. And this 3D IC integration gives us some very exciting applications, like Nano camera from AMS OSRAM company. This is the world's smallest digital camera module. You can see the size of this digital camera with respect to a head of a matchbox. Okay. And what is the job of this? This is used for digital endoscopy. So the endoscopy probe that you put into a gastroenterologist. This is the disposable endoscope, where this goes into your esophagus. It is able to scan the liver, scan your spleen, and real time feed the camera information back to the computer outside, so that the doctor can look at your internal organs and take a decision whether everything is okay or something needs to be done. And like we know, for a photography you need light, and unfortunately inside the body there is no light. Okay, so the camera needs to be able to sense, or it needs to have its own emitter, small emitter, which can also flash its light. All of these integrated in such a small module, and this is the fun. Okay, and such many such applications now form, as an example, if you look at a Samsung S2 and S10 Plus teardown, right? Look at all of these, different companies, Samsung's, Murata, Texas Instruments, AMS, Cirrus Logic. All of these are now taking a share of this whole pie, trying to come up with very, very tiny smartphone modules with all these capacitors, all of them working together to give you a seamless experience for the user. Okay, and this is you can see that this is a cost breakdown, and that's the reason why the more the applications you integrate, of course, there's going to be a cost for the type of features. Right? This is what VLSI can do. Okay, last but not the least, I also wanted to show some skill sets requirement for semiconductor industry, because some of you would want to join semiconductor industry later on in your careers. So, it's unbelievable that the type of people that you need to do a project. Marketing, product architect, lead designer, analog IP, digital IP, layout, mixing verification, production test, procurement, project management, package, ESD, EMC, product manager, reliability, application, sales, quality, all these, and then multiple amounts of people in all these skill sets are needed to generate one product, that one IC that goes into a production, and several hundreds of those ICs now typically make an application or a mobile phone. So each IC or a product is a cumulative hard work of anywhere between 15 to 1,000 highly skilled VLSI engineers. With that, I want to talk about the my last slide. So the CAST Society, because I'm a vice chair of the CAST Society, we are hosting all the CAST chapters of Hyderabad, Bangalore, Kolkata, Delhi, across the country are hosting 19th edition of APC CAST conference. This is happening from 19th to 22nd November in T-Hub in High Tech City. First time in India. It's happening right next door to us in High Tech City. It's a flagship Region 10 conference happening first time in India, and we expect about 300 plus delegates. Footfall, hardcore technology folk conference on circuit systems area. Very strong local industry and university participation, and it's happening in T-Hub High Tech City. 18th November, there's going to be a pre-conference workshop. 19th November, it's a tutorial day. The tutorials will be published next week, so it'll be very interesting to attend some of these, because this typically tutorials give you a very in-depth overview of a certain topic, and this is given by the experts across industry and academia. The actual conference is from 20th to 22nd November, and yeah, we are proud to be associated with T-Hub to be able to host this conference in T-Hub. So the registration portal is open. Please spread the word, register, utilize this opportunity to learn more about the field of circuits and systems. So my last statement, it's no longer only about circuits. We cannot work in silos. It's all about circuits and systems. It's all about the multidisciplinary understanding of how the systems work. And then, it's all about working with different teams and different skill sets. Okay. Thank you so much. I would be happy to take a few questions. Hello?
Yes, sir.
Yeah.
Are you please have any questions? Please ask. Sir is here.
No, I know I rushed through a lot of this, but hopefully this gives you a feel of what VLSI industry is, how exciting is, how cool the VLSI is, and then how niche this field is. It's not easy to be a VLSI engineer. It requires a lot of experience, and it's a daily learning process. And yeah, if this motivates you to join the VLSI industry, then fantastic.
Yes,
Good morning, sir.
anyone have questions? Yeah.
Good morning, sir.
Yeah. Hi. Good morning, Anurup.
Yeah, sir. How, sir? Can you tell how undergraduate student should focus? What particular aspect we should focus to master this particular industry or particular this domain?
Yeah, I mean, since it's a very good question, and I'm sure there are other people who might want to ask the same thing. See, first of all, you would have seen that the level of skill sets that we need in designing this product needs in-depth understanding of all your courses. Control system theory, the electrical circuits, electronic circuits, device physics, control system. So so the courses that you're doing, you have to be very strong with your basics. First thing, and second thing is that of course. I mean, it's a field where I don't say undergraduate kind of graduates cannot be part of this industry. Of course, there are many in the skill sets that I've shown. Right, there are many skill sets where you can probably get trained after being undergrads. My personal preference would be that I always strongly suggest that don't limit yourself to a BTech, because the the reason being that what worked, my opinion, what worked 10-20 years back is no longer working. With all these chat GPTs, with all the automation, with all the intelligence, the AI, the machine learning, right? The mundane skill set, the routine skill set that is needed is now gone. There's no requirement anymore with all these chatbots, and so you don't need, like, the call centers is now replaced with chatbots completely. So I don't think while undergrad gives you a flavor of all the basics and the diversity of the field, you have to pick a specialization. And my strong guide suggestion would be do masters. Do masters. It can be anywhere. It doesn't need to be outside in US. It can be in any one of our institutes here in the country. There are great universities in the country as well. Pursue masters, because that will give you the actual feel or a formal education into the in-depth training on certain specialization. Because you will, by going to masters, you will already narrow down your choice into, okay, am I taking an embedded thing? Am I taking communications? Am I going to an embedded side, or a VLSI design, and so on? And if that inspires you, of course, that will only prepare you well for industry. And further, it's a never-ending topic. So you can also join industry and then pursue a further super specialization on a particular topic. So it's like saying, if you are an same thing, think about doctors. And if you are an MBBS, right, versus if you are a cardiologist in some hospital, right, you have a problem, whom do you want to prefer to go to? So that super specialization or that formal course or a training will always help you to understand more about the limitations, to give you confidence about solving problems. Again, most of the problems that we face today in industry don't have textbook solutions. So it's while textbooks are giving us the basics, it's the creative intelligence of several hundreds of people who come up with solutions, smart solutions, working as a team and then solving a problem. So this problem solving ability, or the root causing ability of a problem, right, that is what you get from a formal education. So while I would not discourage you to pursue an industry job after undergrad, my personal preference would be, please pursue masters, go through in-depth career. And see, one other important thing is, this field needs little patience. Like, we hear about Facebook, Google, and some other thing where some people are offered this packages and that package and so on. That's fine. That's great. But the majority, median, we should not benchmark that. Those are more the extreme cases. If you have to be in the mainstream technology thing, right, you have to have a little patience. Go through the grind, learn your courses, learn your basics properly. Have a little patience, because eventually, believe me, a good VLSI engineer is worth his or her weight in gold. Absolutely. Industry loves great VLSI engineers, creative people, and you can have an excellent career, a very well rewarding career in this industry. I hope that answered your question.
Thank you, sir. Thank you very much. I also have another question. Like, when you are studied, like when you are as an undergrad student, you have learned some technologies which are at past, like they are about before 10 years, right?
Hmm.
Uh,
Okay.
like uh, those who have learned before 10 years are not there right now.
So the technologies might be changing, but for example, like an RC filter, right? How an RC filter, the step response of an RC filter does not change, and this is relevant in any technology. How an inductor behaves, how a capacitor behaves, how op-amp behaves, how a flip-flop behaves. The counters, the multipliers, synchronous logic, asynchronous logic, memories, 60 RAM cell, RAM, ROM. So these basics, they don't change. What is changing is how densely you're able to pack, what technology you're using to manufacture them. So this is what is changing, but the fundamental concepts, they are not changing. So and it's not always about, don't think that it's a 3 nanometer technology, something fancy is happening there and so on. Some quantum those are also important. All this quantum computing and so on, they are great, they're happening. But the mainstream, because the number of jobs that are available in such niche fields are very, very less. If you have to be in the mainstream, VLSI, you have to have your basics very, very strong. So don't ignore any course. In fact, I can give you my own experience. I wasn't a big fan of electrical motors, motor control devices in my undergraduate study. So unfortunately, I did not focus well on that subject. 10 years later in industry, I was asked to design a efficient controller for a BLDC motor industry 10 years down the line. Then I went back, looked into my electrical motor textbook, and then started understanding that better. And I wish I thought, maybe in my undergrads I wished I focused more on the course. So you never know where you end up with in your whole professional career. So at least have your basics right, and be learnable. So this means most important, or I would say the most underrated skill set is ability to do self learning. Don't expect that professors or teachers will teach you everything, and by the time you come out of your university you are equipped to face this world. No, most important ability is to do self learning. The information is available now. You have everything, NPTEL, YouTube lectures. There are several hundred thousands of lectures, materials available online. We just need to be patient and download them. Once you have downloaded them, it is your ability to self learn, to learn them on your own, read through, go back to the basics, refer, persist with that, try understanding, discuss with your friends, discuss with your faculty members. Your ability to self learn, that is what will take